In this video, we'll determine the electric field for a few special cases with planar symmetry. Now remember that for an infinite plate that's positively charged, and at some distance from the plate that's very small compared with the dimensions of the plate, we found the electric field was the areal charge density on 2 by the permittivity of free space, and that was using Gauss's law. And that was given that the point is sufficiently away from the edges of the plate. Now suppose we have this case of 2 infinite plates that are positively charged, and the distance between these plates is quite small relative to the dimensions of the plate. So if we want the electric field at a point between those plates, well, as we can observe, the electric field vector due to the red plate points upwards, and the electric field vector due to the blue plate points downwards. So therefore the electric field at points between the plates and sufficiently away from the edges is 0. And suppose we want the electric field at a point that's above the positively charged blue plate. Well, in this case we have the electric field vectors pointing in the same direction, and we assume they're the same magnitude because this distance is still sufficiently small compared with the dimensions of the plate. So therefore the electric field is a superposition of the electric field due to the red plate and then plus the electric field due to the blue plate. So that's effectively equal to sigma on epsilon naught. And similarly on the other side over here, you're going to get the same result. And I encourage you to actually verify this using Gauss's law by constructing a Gaussian surface and exploiting planar symmetry. Now suppose we have this case where one of the plates is negatively charged. Well, in this case the electric field vectors are going to point from the positive to the negatively charged plate. So between those plates, using the superposition principle, we're going to get sigma on epsilon naught, as we did for this case, but between the plates. And this configuration of plates is reminiscent with a capacitor, which we'll explore in subsequent videos. Now similarly, outside these plates, so if we look at a point outside the red plate for example, well, as we can see, the red vector due to the positively charged plate points downwards, and the blue electric field vector due to the negatively charged blue plate points upwards. So these cancel out, and the electric field outside these plates is effectively 0. And I'll see you in the next video.